So this is going to be a talk. Maybe I should start by asking if anybody knows what the Lightning Network is or how it works. If you do, please raise your hand. Okay, so we have like 4 people. So for the rest, I hope this will be interesting. So maybe I should start with kind of a call to arms, since I'm speaking to mostly networking people here. Blockchains and cryptocurrencies are an area that a lot of security researchers initially started looking at. And really there are a ton of crucial networking problems everywhere in this space. So if you're not working and you're not familiar with blockchains, you're not working on that, I urge you to have a look, because there are a lot of things that you can a lot of classic networking problems that you can revisit from this perspective. And I think I'll show maybe one corner of this in Lightning networks. And there are a lot of really crucial problems. Pretty much the latency in block propagation in Bitcoin is what causes problems with its consensus protocol if you try to scale it up. So Bitcoin's scalability problem is really related to latency. There's a lot of stuff about you could do on the layer of how blocks are even relayed and propagated. There's a peer-to-peer network that gossips transactions and blocks in Bitcoin, which is insecure. There's a lot of stuff to do about the way miners generate their infrastructure. And this is just Bitcoin. There are a lot of new cryptocurrencies and a lot of new other ideas. So there's a lot of stuff to look at. But I'm really going to try to focus on one corner of this world, and I'll show you a host of networking problems in there. And this is the off-chain payment channels area. So this is a system in Bitcoin. It's called the system is called the Lightning Network. There are variants in other cryptocurrencies. If you've heard of Ethereum, Ethereum has something called Raiden, which is the god of lightning. And so all of these are really an instantiation of this one idea of off-chain payment channels, which I'll explain in the talk. So maybe we should start with why Lightning channels came to be. They came, as a response to a problem, and the problem is that blockchains don't really scale well. When you start to increase the transaction throughput in Bitcoin, Ethereum, and others, you end up with larger and larger messages that you have to broadcast. Blockchains essentially synchronize data between a lot of different computers. This is what consensus protocols do. So when you have a lot of data on the blockchain, you have to send it to many, many computers out there. Thousands of computers have to do it fast, have to get it right. The fact that it's accepted by a large number is what causes consensus protocols to work. And so this inherently slows down consensus. So there are 2 main approaches to do this. One is to kind of think of other consensus protocols to get that on-chain capacity to do more stuff on the blockchain. And other solutions are to just take things off of the blockchain, just have fewer and fewer transactions and still manage to do things. So the Lightning Network falls into this second category of doing things off-chain. So I'm not going to get into how Bitcoin works and how blockchains work. I'm going to take that as a given primitive that doesn't do much. It's just, putting things on the blockchain is going to be equivalent to just publishing them. There's really no difference in a way that everybody can see, and we can take things that we publish back and erase them. But that's pretty much the only thing that blockchains are going to give us. And I want to start with an example of something called a One Directional Channel. This is maybe the simplest idea that we can, the simplest construction that we can give for the Lightning Network, maybe, primitive that we later use to construct the whole network. So what we want to have is Alice and Bob are 2 participants who want to pay each other money, and they meet up frequently. So Alice and Bob, really, maybe Alice wants to pay Bob every day. She goes to the store and buys a stick of gum. And if this was the usual world, she would just have to post a transaction onto the blockchain saying, she gives money to Bob, and then that takes a while. In Bitcoin, blocks are mined every 10 minutes. So it'll take at least 10 minutes until something happens in the blockchain. So Bob will have to wait a while before he gets his money every time. And what we're really trying to do is do better. So as the first step, Alice is going to do something. She's going to set up an account where she puts in 1 Bitcoin. And money in this account is redeemable under one of 2 conditions. One condition is if Alice and Bob both sign a message saying, here's how you can take the money, right? Then that will release the funds. Either right, Alice and Bob together sign it at any time, or we can make it redeemable by Alice after 1 week. Okay, so the reason for this second condition is that if Bob suddenly stops cooperating, we want Alice to have her money back. If he disappears or he turns out to be malicious, Alice, she put in her money. If it was just redeemable by signatures from Alice and Bob, this would be a problem for us. So now this gets placed on the blockchain. So essentially, Alice just paid 1 Bitcoin into this account. And now she can send Bob messages on a direct line without sending anything to the blockchain. Basically a message saying something like, we agree to split the contents of this account where I get 0.9 and Bob gets 0.1 Bitcoins. And she signs this cryptographically, sends it to Bob. And now, right, so Bob has this thing, he can always add his signature. And if he sends this to the blockchain, this meets the criteria in the account to redeem the money. And now essentially that means that he's just received a payment of 0.1 Bitcoins. But instead of sending this to the blockchain and redeeming the money, Bob actually decides to hold on to this because if you recall our initial motivation, we're trying to avoid touching the blockchain too often. He still has a whole week before Alice can take all of the money. So he waits a while. And then Alice maybe gives him another transaction. Maybe the day later, she comes in to buy another stick of gum. She updates the split of money. She says, I'm willing to take 0.8 Bitcoins and you can take 0.2. And here's another signature. And he gets another message. And now Bob essentially can discard this one because it gives him just less money. There's no use in keeping this old transaction. So this is kind of a replace by incentive. He only has an incentive to keep the latest one. And essentially he's just gotten another payment of 0.1 Bitcoins. And again, we didn't touch the blockchain. Okay, so that's maybe the crucial thing. Is everybody with me? Any questions thus far? Okay.
So far, is that like something new? Is that like things that already been proposed in the past?
So this was not part of Bitcoin's initial launch, but very quickly people understood this idea of one directional channel. The next development that I'm going to show you is a two-directional channel, and then maybe the next step after that I'll also show is due to Poon and Dryja from Stanford, who proposed to actually combine channels together to a whole network. And this is something that's actually deployed. Okay, so this is a deployed system. There's code running. There's a kind of an RFC. They call it bolts. For the protocol, so everything is fairly documented. And what I'm going to talk about is basically what issues come up with the system. But for that, we need to understand how the mechanics work. So this is a real system, and it's actually running. Currently, there are something like I think $8 million locked in funds locked into this. Is not a lot of money compared to the whole amount of Bitcoins out there.
So what happens if the order of messages was reversed? I paid you too much, and then I realized that. Or
there's no way to withdraw to retract money here. This payment once it's done.
I can't send this first message after.
She can send it, but Bob's not gonna replace his old one because this gives him more money. So this is not a secure way. At least in this construction doesn't give us anything. But very quickly we'll see that Bob can return some money to Alice with a slightly different construction. So the properties of one-way channels are that at any point in time, Alice and Bob can claim their money, right? Alice has to wait if for a week if Bob disappears. So it's not immediate. But he can always she can always ask him just if he's cooperating, please claim the funds on our last transaction. Let's close the channel. But if he disappears, she can always go back after a week and even have more money than she gave him. There are only 2 transactions per channel: one to open it and one to close it. Right, so we wouldn't do this if we're just transacting once, but if we do transact repeatedly, this is worth it. Payments are essentially fast. Instead of waiting for a block to accept our transaction for 10 minutes, once I receive the message, I'm in effect guaranteed to have the money, right? As long as the blockchain will later pay me. And so what we can do here is micropayments, right? All it takes is communicating over the internet between Bob and Alice. So the limitations of this construction that I've just shown is that channels actually run out of money after all the money is assigned to Bob. I mean, this channel has lived out its purpose, and we have to close it. There's nothing else to do. Their payments are one directional. And maybe we should also say it has an expiration time of a week, right? But this is actually not a hard limit. There's a way to avoid that. So what we really want to do is two-way channels. Yeah?
Are there race conditions at the end, technically?
What race conditions, for example?
If Bob publishes a payment he has gotten at some point, which is very close to the deadline, and Alice tries to
send him another one?
No, to go up and take the money, and then technically whatever happens first.
So Bob just takes, a day before this week is over. Bob says to Alice, "Thank you. We're going to close the channel." A day before.
I mean, in the network, like technically, I can maybe double spend that way.
How can you? I'm not sure I understand how you can double spend.
Alice will try to. Well, maybe it's negligible, but Alice will try to both take her money and pay. The same thing will happen with Bob, and then whatever happens first.
So Alice can't take her money alone on her own, right?
No,
she has to wait a week. But then we never get close to that end of the week. Bob will not accept anything. After 6 days, he's going to say, "I want to close the channel. I have a day to get my transaction into the blockchain. It takes a while, so I'm just gonna take some safety distances here."
They could collaborate though, in order to double pay.
No. This money, there's only this money in the account, right? They're not going to be able to double spend it. Either Alice gets this money or Bob gets this money. If they collaborate, they decide on a different split. But there's no more money than what Alice initially put in, right? The blockchain doesn't create money for them. It's this money that Alice deposited at the beginning, right? That they're splitting. So there's no. The only thing that they can do is cheat each other here. Or they might try to do, but it doesn't work, of course. So now what we want to try and do is to have two-way channels. So Alice can give money back to Bob, and Bob can give some to Alice. And using one-way channels, I think you should almost instantly see is not the best thing, because if we start with 2 one-way channels, where Bob sets up one where he has 1 Bitcoin on his side and he can move it slowly to Alice. Alice can move the money slowly to Bob. Then after a while they move some money. Eventually they will end up at this state where all the money here is moved to Alice, all the money here is moved to Bob, and they're stuck. But something feels wrong because we started with 1 Bitcoin on each side. We ended up with 1 Bitcoin on each side, and now we're stuck for some reason. Obviously we should be able to still continue to transact. So this doesn't work. We need a different construction. And here's that construction, of course. Alice and Bob create a joint account. Each one puts in a Bitcoin. And this is redeemable when it's signed by Alice and Bob at any time. Okay? So maybe this is also a warm-up with our first attempt. And they also create a transaction before they actually publish this to the blockchain. They do this first. They agree to do a 1-1 split. That the money will go equally to both of them. The reason they do this is just in case one of them disappears after they lock in the funds. then the other can claim his part, his or her part. And now they can start again sending these messages. Maybe Alice tells Bob, I agree to send you 0.1 bitcoins by adjusting this balance, 0.9 for me, 1.1 for you, and she signs it. And now Bob has this newer transaction. He can throw out this old one, gives him less money. But there's still a problem here. So can you spot the problem?
Involved in these signatures? Or,
No, it's not time-stamped.
So Alice can get.
Or timestamps are also kind of lies, right? I can put anything I want there. There's no service to
But as long as
timestamp.
the other side also signs it, it means that the other side acknowledges that the timestamp is correct.
Sure, but so what's the problem if you can? Yeah. Yeah, Alice can always, like, before sending, she had a higher balance. She still has that message that allows her to claim it, right? So we're in a problem that if Alice can always claim to have money at any point in time, she can later ignore messages that she sent that are signed. She has older messages that she can replay into the system, right, and get money. So we somehow need to, right? She would prefer to send this, and we have to revoke this old transaction, right? That she had. So how do we do revocation here? One way to do it is to change the deal that they are signing here, to this contract, to say something like, we agree to split money, one for Alice, one for Bob. This is kind of the setup transaction. It's going to be redeemable after 1 week if it's not appealed. Okay, so if you post this to the blockchain, you're not going to instantly get a Bitcoin each. You have a week of an appeal period. And we'll see what appeals actually do. There's a serial number here. It says this is transaction number 0, right? And now each one of them is going to hold this transaction. You can appeal within a week with serial number 0. And when Alice sends money to Bob, she says, I agree to a split. Here's the new split of money, and it's also redeemable after a week. And here's this new serial number, which is higher. So this is you intuitively thought about timestamping, but this serves the same purpose. This kind of says this message came after this one, and so this is newer, and we have a week to appeal. So what does an appeal do? Basically, I show a signed message by the other party with a higher serial number. That means there was a newer state that we agreed to, and so we can claim money. Right. So Bob throws this away. Alice also should know by now that she probably won't get this money. Bob can be gracious and sign this and return to her, so she has the latest state. But even if he doesn't, and she ends up sending this to the blockchain, he has a week to appeal. Right? Yeah.
How do you implement these appeals?
In Bitcoin? In Bitcoin or in Ethereum?
Bitcoin,
So in Ethereum, you literally have a smart contract. You can do anything you want in code, right? In Bitcoin, there's really, what you do is you have an output that's locked in time that has, right, the Bitcoin scripts allow you to do something. You can say either, I can take it, Bob can take it after a week. This is the, holding this, right, the time lock. Or Alice and Bob, together signed on a transaction, can withdraw from that output. And to do the revocation, they actually also send a transaction that allows you to steal the money from an old one. Right? So if Alice posts this, she has a Bitcoin that she has an output with a Bitcoin she can take in a week, or this Bitcoin can also be taken if Alice and Bob have signed a message together.
I see.
So she needs, when she sends this to Bob, she also sends him a message allowing him to steal this Bitcoin specifically, and that effectively revokes
So
it.
that means that Bitcoin cannot be spent for a while. Like,
For a while,
it's
yeah.
even further than.
Yeah. And actually, if you think about it, Alice and Bob, even when they're right, there's money in Alice's side of the account, she doesn't want to send it to Bob, but they don't close the contract, right? So all of this money is locked in between them. It's not going anywhere. None of them can use it, really, except as liquidity that's ready to be sent to the other. So we'll talk about that as well if we can make it to that slide. So now Bob, of course, can send new messages with higher serial numbers and also effectively revoke the previous one. So let's discuss the issues with this construction. So again, we have something that we need to notice. The amount of money that we put in is kind of trivial, constrains the use of the channel. If all of the money has moved to Alice's side, she has a Bitcoin, Bob has 0, of course he cannot send her anymore without replenishing the channel or adding or using another one or using a blockchain transaction. So there are limits to the, right? We have constraints on how much money we can send. Right, to rebalance the channel, we have to put in more money. So it's a blockchain transaction. It's expensive for us. Communication between Alice and Bob is relatively cheap. And also, what we also need to do is the participants need to be online once a week here to submit appeals. If the other party closes the channel without your knowledge on an old state, you have to be there to kind of catch them and appeal. So this is actually something that people have been addressing. There are now services called watchtowers that allow you to submit this thing to another server that will appeal on your behalf. You also have a receipt that you submitted it to that server. So if that server doesn't appeal, you can later come and say, here's your. You had a duty to perform and you didn't do it, and you have all the entire the paper trail to show that they did not appeal on time.
It should be hard to automate this thing, right?
Sorry?
To track.
Yeah. So
To automate.
it shouldn't be hard.
Track the blockchain.
Yeah, and you also have so people made sure that you have all the receipts to make sure that I submitted it to the server. I can prove that I submitted this request to monitor my funds, and here my funds were stolen and not appealed by the server, so I can prove this in a cryptographic way. So all these things are there. Some more issues are interesting. Let's assume that Bob's computer crashed. Right, or his phone, maybe his phone, you drop it into the toilet or something by mistake. All the data there is gone. But luckily, Bob backed up his machine, and he has some transaction signed by Alice that gives him the money, right? So is this okay, right? Think of what happens if Bob replays an old transaction. He's actually using one that will trigger an appeal by Alice because he doesn't have the latest transaction. So in our scheme, it's not that bad because Alice will appeal, he'll get the right amounts. In Bitcoin, because of the revocation mechanism, actually he's going to lose all of his money. Right? The revocation mechanism allows Alice to steal all of the money from the Bitcoins that he cheated on. So it's kind of bad if you restore from a backup and you lose all your funds because of that. Kind of a nasty thing. Okay, now we also have the week for appeals. I mean, if they're both cooperative, they can of course not wait the week. They can sign a message saying we agree to close the channel now with this balance. We don't have to wait for the appeal period. The appeal period is if one of them closes the channel unilaterally without the consent of the other. So we don't really have the week to wait. Okay, so this is where we get to the networking part, right? So this was the link level protocol. Now we're going to get to the network. So now, maybe the first thing you'd notice is that whenever Alice wants to pay someone, she can't open a channel just to that person. It's not worth it for a single payment. And there are too many people that we buy things from, right, every day. It's like laying down your communication line to talk to every person you want to send a message to. Right, that's the equivalent. So what we ideally want to do is if Alice is connected to Bob and Bob is connected to Charlie, we'd want money to move from Alice to Bob, from Bob to Charlie, right, on Alice's behalf. So this is where it starts to get a bit more interesting. Right, so we'd want to do something like this, adjust balances where Alice drops her balance by 0.1, Bob increases here and decreases here, and Charlie gets a little bit more money, and now this effectively is a payment to Charlie. So the question, of course, is when we're talking about money, who goes first? If Alice gives the money to Bob and then asks him to forward to Charlie, he can steal the money, not pay Charlie, and just disappear. This is a problem. On the other hand, if she asks, if we ask that Bob pays first to Charlie, then Alice can, not pay her dues to Bob. Charlie already got the money. She's very happy with this. So we have to do this atomically. And the trick that is used in blockchains is the following one. It's a very clever trick. Charlie and Alice meet up. Probably she walked into his store. She wants to pay him to buy gum or something. So here's the protocol they run to get the payment. Charlie thinks of a secret S star and computes a cryptographic hash of this secret. Right? So H star is the hash of S star. Some one-way function. And now Alice now can pay Bob. She can send him a transaction saying, I agree to a new split of the channel, 0.9 for me, 1.3 to you. She signs it. And there's a place here that you need to write the secret. And this transaction is considered valid only if the secret that you provide here is the pre-image for this value H star. Right? So Charlie tells Alice what H star is. Bob can basically claim the money only if he knows the secret. So at this point in time, Bob does not know the secret. He cannot claim the money, but he still holds on to this transaction. Now Bob says, yeah.
Silly question. So this three-way transaction, what could you give an example? Why is it that bilateral transactions aren't enough?
Yeah, let's say, I walk into a gas station, I want to buy something, right? I didn't open a transaction channel with that gas station. I have a transaction channel with someone else. I want to use it to pay, right? I can't open a transaction channel with every store that I'm going to visit once. So I want the connectivity, so what this will allow me to do is to connect to one place, one provider. He's going to have a network, right? I have one link, and I can now suddenly pay to anyone who's connected.
It's also a commitment problem because you want to pay to 100 people and you don't have 100 bitcoins to spend, right?
Yeah. That's a liquidity issue more than anything, right? There's no physical limitation, right, on establishing channels with the entire world. I mean, if I have the memory and the disk space and the communication, maybe I can do it. But it's really an issue of cost of liquidity, right? I need to take money, lock it in a way that it doesn't give me interest. Maybe I have to borrow it, right? So I'm losing interest payments.
That seems like an underlying limitation of Bitcoins and cryptocurrency specifically, right? In the real world, right, I would have paid the gas.
No. So these are promises that are trustless only because we've fully collateralized them, right? In some sense, only because the money is locked. This is a cashier's check, right? When I give you a cashier's check, the bank is actually holding some of my money in my account locked until I return this cashier's check and they rip it up themselves. Otherwise, I can't move this money. So effectively, this is locked money and I'm losing interest payments on it, always. This is not a limitation of Bitcoin. It's any financial system would have the same problem.
It's somehow like the fact that I don't want to open a new transaction to go on the Bitcoin for every person is the reason.
But that is the limitation.
The limitation is you don't want me to double. No, so you don't want me to double pay. In the regular banking system, I can give out checks, right? Regular checks. Regular checks can bounce. This is an issue. Regular checks are like double spending. If I give this, I have $100 in my account. I give out 3 checks for $100. 2 people are not going to get money. This is the same as double spending in Bitcoin. Here, Bob can hold Alice's money. She holds a check. Why does she know that she has this money? Because it's a cashier's check. It's guaranteed by money in the bank that's locked specifically for that purpose. That's exactly the same thing as cashier's checks. Right? So it's amazing how these ideas, when I explain it to people, to regulators, I tell them about, these are cashier's checks, and the signatures are just, signatures on the check, and amounts are amounts. Or essentially, this computer science reinvents everything from finance in our own language and using our own tools. Right? They don't use hash functions in checks at the moment, at least. So now we want to somehow guarantee, right? So I hope I convince you that at this point Bob doesn't know the secret. He can't withdraw this money. He doesn't know the pre-image to this hash. But he feels secure enough to do something like this. Now he agrees to give Charlie a transaction that says, this actually needs Bob's signature here, which I'm missing for some reason. He agrees to give Charlie a transaction that is signed by Bob and says, if you provide the secret, you can take 0.1 bitcoins. And why does he feel safe enough to do this? What happens if Charlie closes the channel and provides the secret? Right? Bob loses money, but
he can also redeem that.
But he can also redeem that because anything that is put on the blockchain is essentially broadcast to everyone. So if Bob loses this money to Charlie, it's only because this secret has been published on the blockchain, and then he can put it here and claim this money. Okay, so this contingent contract made him feel safe enough. Of course, Charlie does have the secret. He came up with it. So Charlie says, I already got paid because I can't publish this transaction at any point in time. Now he says, I got money. I can be a nice guy, and I can give the secret to Bob. Now Bob got paid. He doesn't have to wait until Charlie publishes this. And he can show it to Alice. And now they can send another transaction just like this, but without the requirement for the secret if they want. It's completely equivalent, and everybody signed.
Once a single person cashes out, everybody cashes out, I guess.
Exactly. Exactly. If somebody closes the channel, again, this is a unilateral closer of the channel. They can always close the channel and not publish the secret if both of them have agreed. And Bob will only agree after Charlie told him the secret, so he can use it elsewhere.
Why does Alice care for the secret?
Alice cares for the secret, like if she wants to close with the state, with this newer state, right?
Oh, I see.
But she doesn't, we assume she's honest. Yeah, we assume she's honest and everything's fine. But I mean, she gets the secret, and what really would happen is she sends Bob another transaction without this secret. Because one of the things we'd have, let's say we have a lot of transactions like this going through, we'd have a bunch of secrets starting to pile up here in the channel. And so when we send them back, we can actually start removing them from the contracts. That's the mechanism.
And Bob needs to publish the second contract with less time, right? So that he can both get the message and publish the previous.
Yeah, so we'll talk about expiration time in a second, about time, yeah. So appeal periods are all the same, that doesn't matter. There doesn't need to be more time. Right, so maybe this is the point about channel establishment and disassembly. One of the things that can happen here is that Charlie doesn't claim the money, ever. He doesn't publish this, he doesn't give the secret. So we have this transaction between Alice and Bob that still exists with this contingency on the hash. And now later maybe Alice tries to send money to Bob again. She needs to adjust the money. Some of it will be contingent on knowing the secret. Some of it would be just another change in balances, etc. So the contracts start to get a bit messy. What we'd eventually want is to have a time where we can remove this secret if Charlie failed to send this. So there's also a timeout on these things that I'm not explaining how. But then again, you have to make sure that this times out before this, because otherwise Bob might lose his money to Charlie without having a place to draw money from. So this is all the mechanics of Lightning channels. So now here's the a screenshot of the entire network. People who are doing measurements, you don't have to do a lot of work to do measurements in Lightning because nodes actually gossip about all the channels that are out there that are routable through. We'll talk about why in a second. So we have a good picture of the Lightning Network. We know how much money is in each channel. We know about the time they wait to expire. We know a bunch of stuff about the network. Last time I looked, $8 million in Bitcoins. I think I looked around May. And in January it was half the amount. So in 4 months this network doubled in the amount of money in there. Bitcoin did not double in value at that time, right? So this is growing. There's some adoption. There are 3 implementations by different companies who are all coordinated on this RFC for Lightning. And maybe with my last 10 minutes, what I'll try to do is give you some of the networking questions behind here, right? So we have now a payment channel network where we can pay anybody we want as long as we're connected. And the question is, right, who picks the route, which route is picked, right? Right? How do we learn about new channels? What's, all these things we ask in regular networks. Can transfers fail? What do we do then? What about privacy? Can we see the payments of everybody? Right? Is everything just in the clear? And I can tell you the answers for the current implementations. So the current implementation is to have source routing. Really, if Alice is paying somebody here, then she picks the route. And to be able to do source routing, you have to have knowledge about the entire network, or a good deal of it to be able to pick a route. So which route is picked? So usually you're looking for something with minimal fee. These guys on the middle actually don't transfer the exact amount that they got in. It's not the exact amount going out. They keep a small fee for being intermediaries. So you're looking for a low fee. You have some penalty for hops. You have some penalty for channels that are short-lived and are about to expire. And you usually add some noise to not always route the same way. And the reason for this noise is because, right, if you always routed the same way, one of the nodes could be offline, not communicating, or could just have no liquidity in the channel available at the moment in the direction that you're trying to send. So payments can fail, and then you have to reroute. So this is what, you introduce some noise to pick a different route every time. Yeah?
Question about this. Can you actually kind of have a transaction and split across two routes? Is it possible? Or does it make sense in this context?
It makes a lot of sense, but you need to think about how you would construct it with secrets, right? So there's an interesting paper by Maurice Herlihy on how to do these things and how to break up the secrets and what you require. So sometimes you would require that the XOR of two secrets that you get is the thing that's right. So you need to combine secrets in order to withdraw money. Sometimes you need to split. There are all sorts of different tricks for that, but nobody's implemented that. So it's the very simplest thing. I guess like routing on the internet is just use the one path. That works. It's failure prone as it is. Going on over multiple paths has issues as well. So I think you can see all the problems that you already know and love from networking world kind of manifest here in some twist with liquidities instead of capacities and some other behavior. Right. So learning about new channels. Apparently, there's another peer-to-peer network. So if you're running a Lightning network, what you usually a Lightning node. Right, you have one of these machines who has channels. You usually have another Bitcoin node next to it. The Bitcoin node has a peer-to-peer overlay where blocks and transactions get sent. The Lightning node has a different peer-to-peer network where basically channels are gossiped about. So everybody gets a picture of the entire network. And there's another network on top of that of channels, which is completely separate from these two peer-to-peer networks. So everybody's connected with three different overlays here, all the participants, which is really bizarre, right? Transfers can fail, right? Because nodes can just not respond, or the channel state can be unbalanced in some way, and then you just try to reroute again and hope for the best. Not the best thing to do, I think. And privacy, if you think about it, this does use, right, we're using source routing. The idea here was actually to do source routing because you could do onion routing, something like onion routing, where everybody just encrypts all the messages, so you only know what next hop you wanted to send this packet to. And so channel establishment, if you recall, is built slowly along the channel. There's really a message going through where each node decrypts its own part and knows where to forward next. And so as this thing travels, it might eventually figure out that some link is unavailable, you have to fold it all back and reroute and try again by the source.
So Aviv, is 1 week like a standard time?
I was just saying a week. Actually the default is a day. It's 100 in Bitcoin. It's 144 blocks, which is roughly a day. They always count it in blocks and not in time because blocks are reliable.
Yeah.
So it's 144.
And is the fee stable for that amount of time? Yes.
Fees are typically configured into nodes at the level that you establish a channel. It's there for life. Right? Channels don't expire here really.
Yeah, but I'm thinking, well, there's a transaction that I might have gotten like at the beginning of the channel, and now it's the end of the channel, and that's the only transaction I have, and I really want to redeem it, but maybe the fee is now too low to get.
Transaction fees for the blockchain. You're saying?
Yeah. So
yeah, that's another issue. We know that fees are not stable at these time periods, but there are mechanisms that allow you to increase the fees after the fact. Child pays for parents and things like that. It's for Bitcoin. So that's another mess. What you might be worried about is that when the appeal period comes, the network is too congested to appeal. And people are thinking not about a collapse of a single channel, but maybe let's say there's a cascade of collapses or something systemic happens, and everybody wants to appeal channels at the same time. Then it's very costly and it's very problematic, and you just leave the money, right? So that's a possible attack, right? So maybe one thing that I've done, one of the works that I've started doing is looking at the economics of these things. If you think about the lifetime of channels, what happens if, the model we use is that Alice and Bob just exchange coins in the channel with equal probability. So the liquidity in the channel is basically doing a random walk back and forth from Alice to Bob. So it's a model of payments. It's hard to model the demand matrix here, but we thought of this. And then the lifetime of the channel it goes up with the square of the amount of money that you put into it. So if Bob and Alice and Bob both put in money, the more money you put in, the less likely you are to hit these boundaries where all the liquidity went to one side or to the other. So a random walk kind of gives you a square lifetime. And now that you have this lifetime, you can think of what is the cost to fund the channel. I mean, if I put more money into the channel, I have to pay less blockchain fees because I have to pay less these setups and transfers less often. On the other hand, I have more interest payments, higher interest payments on getting more money and locking it up. Yeah.
Why is random walk a reasonable assumption?
Obviously it's not, but I really have no data on.
So just like intuitively from what you described to Michael, for example, you're expecting that you receive payments and you're using this as a brokerage, which would be like credit.
So
wouldn't you expect the payments to be heavily imbalanced towards one side paying?
No. So think of the average bank account of the average person. What does that look like? You get a salary at the beginning of the month, or bi-weekly, depending on every Tuesday, and then you do a lot of small ones. So let's say there are two situations here. Maybe if I have a channel the size of let's say 2 paychecks, then at the beginning of a month it gets a huge transaction in one direction, then a lot of small ones going back, and a huge one at the end of the month, at the next month, and a lot of small ones.
I'm using the channel that I receive my paycheck on and the channel that I spend on the same.
That's true.
Is that really very common? That seems a bit strange for financial institutions.
So this is I'm just giving you my incoming outgoing transactions on my bank account. So we have to think of so transaction sizes are not the same, but the challenge. But what I'm saying is the channel is balanced. If it's not balanced, then you're putting money in savings, right? You're putting money in savings. That's the imbalance. Any imbalance is only you saving money.
I don't understand this bit, right? So I agree that the total amount of money, if you just look at my account, is balanced in
Sure.
number. I don't agree that automatically translates to the channel is balanced. So
I agree.
I might have a channel with Michael and a channel with NYU.
No, I'm not talking about the channel. So what I'm saying is, what is your demand for payments? What are the payments that you want to make? You could do them on the channel, but you can also take a suitcase of cash or do them on the blockchain directly. So what we are actually trying to do in this work was we assume different transaction sizes for individuals, and we tried to see if for large transactions you'd also want to send them on the channel or on the blockchain. And the actual result from the work is that you want to send them on the blockchain because blockchain fees are flat. They don't depend on the size of the transaction. While Lightning channels, you could argue, will and do have actually in implementations, have fees that depend on the size of the transaction. The reason that Lightning Network fees depend on the size of the transaction is that larger transactions shorten the lifespan of channels. Right? If you did if you accept for a moment the random walk thing, larger steps in the random walk make your channel lifetime smaller by the square of the something related to the quadrat to the square of the step size, and so even under the assumption that all of the transactions go through the Lightning Network, and even under the assumption that they are a random walk, and that you're not using channels as one-way things, we were trying to see what benefits we would get for the network under this optimistic assumption. So you have this optimal way of funding channels, and what you get is some demand for blockchain records. And demand for blockchain records comes from two sources. One source is I want to establish and destroy Lightning channels. And another is for large transactions that I don't want to send through Lightning channels, I want to send directly. And those compete with each other. We could compute that, and so we could see where all transactions go. This is showing that nearly, in terms of numbers of transactions, almost all of the transactions in our world went through Lightning. They were of different sizes, but in terms of volume, the blockchain had more volume as we increased the number of users in our simulations. So I'm not going into details on purpose here. Other things that we're working on are some attacks, right? You could start to think of ways to disrupt the gossip protocols between nodes, and so the victim doesn't know about the network that he needs to route through, and so he cannot route payments. He thinks he's connected, but you're filtering channel announcements to him if you kind of isolated him. So this is one very easy attack. There's also kind of the equivalent of a hijacking attack. You can put in a bunch of nodes with really, really low fees. You can promise to route payments with 0 fees. And so this source router tries to go through you. Of course, you always drop the packet. You don't do anything. And then he tries to route again. Again, he's drawn to route through you. You drop the packet again. There's no information about what happened, where it happened. Because this is all Tor-like, he's very likely to go through you many, many times and just not realize it. And so you can attack the network again. Another third attack we're exploring is just to try and open a lot of channels between Alice and Bob, and then Bob just doesn't withdraw the funds. So these secrets start to pile up in all the messages here. There's a congestion effect. This is kind of a congestion attack, trying to create routes and not claim the money. There's a limit to the number of routes you can actually put on a single edge because of that. And if you reach that limit, you're denying service from everybody else. So we're looking at the attacks. Hopefully, the next step should be looking for ways to mitigate the problem. And that's it. That's where I'll stop. I hope I got you interested and I hope I could draw the correlations to networking and to get you to have a look at this very interesting area. Thank you. Thank you very much.
We have a few questions while I'll set up this. So in all of these attacks, the attacker can get away with the money, right?
No.
All denial of service, essentially.
Yes. This is the network. This thing is designed to be. This is also mine. Sure. The network is designed to be completely immune to attacks where you take money. This forced certain decisions on how you establish channels and so on that don't allow you to do things like know if you can succeed in routing, etc. Right? And you can think of other parallels. Why don't we use something like BGP here for routing? Maybe we could, right? This Tor-like routing in the internet, you're routing with, using BGP on the lower layer, and Tor just sits on top of that. So you can still anonymize your payments by using, routing from Tor node to Tor node is via BGP and other, internet routing. So this is a weird choice. There's another thing you could do, right? If liquidity is on the channel moved, you would ideally want to update your routing, but this is maybe too frequent for you to do. All sorts of concerns here, choices that had to be made because of this construction. So if there are no more questions, I'll thank you guys again.
Thank the speaker again. And,